Thank you, everybody, for taking time to attend this presentation. Hopefully, this will be a short, sweet, informative presentation on energy efficiency as it pertains to transformers in your facilities. My name is KClark, as they stated. I'm an electrical engineer by trade, was a consulting engineer, designing buildings, schools, hospitals. I am now a manufacturer's representative with Swimco. We work very closely with facilities managers, energy managers, and engineers on projects to help get the most efficient and the best performance possible of products on projects to help the end users. So again, I want to thank you for attending this seminar. If you have any questions, please jot them down and we'll have a question and answers at the end. But let's get going on this, and again, thank you very much. The agenda we want to touch today about transformers and energy efficiency as it pertains to them is primarily touching on the requirements by Department of Energy, which is the DOE 2016, which is a requirement of all manufacturers, but I want everybody to understand what those are and the ramifications of some of those design or manufacturing practices to meet these requirements. We're also going to touch on K-factor ratings, which is actually a rating applied to transformers for the loads that they will serve. This is an important topic. However, it is also somewhat misled topic. So I want to make sure everybody understands what it means and if there are any issues that K-factors may play in product. Third is the transformer application. That is primarily, how do you apply them, what loads they serve, what you need to be aware of. We'll go through transformer options, some options that a lot of customers may not know exist, but we highly recommend some of them for the ease of your use. But we'll touch on a few of those options and then finish up with some what we call power distribution units, some ideas. They still have, they're involving transformers, but they allow you to save space, make a cleaner install, save install time from the contractors, an array of opportunities with those. We'll just touch on a couple of slides on those. And then it's not on this agenda, but there's some spec criteria to kind of sum up what we talked about and be able to tell you, here's what you need to look for when it pertains to transformers and making sure that you get what you specify or what you ask the engineer to specify for you. So Department of Energy 2016 became effective January 1 of 2016. And what happened is the Department of Energy realized that transformers were a major energy loss within facilities. With the energy efficiency mandates being set forth by the federal government, local governments, what have you, Department of Energy decided that they knew there was a process or the ability to build a more efficient dry type transformer that goes inside facilities. They worked with a major manufacturer on these designs and how do you design or build a more efficient transformer. And as everything, if you build product to performance or specific performance, typically the product becomes more costly. It's just a drawback of using better materials, better manufacturing processes, that all costs money. So products tend to increase in price. And when this went into effect, transformer pricing did go up. However, what we'll kind of point out is the Department of Energy was short on some of the requirements and also on making sure the manufacturers were holding up to those requirements. And we'll touch on that. So what the goal was with Department of Energy was to try to receive 30% less losses, meaning make the transformer 30% more efficient. In doing so, there's ways to manufacture that product or design and manufacture it such that you can make the unit more efficient. You can go further and make it even much more efficient, what we consider ultra high efficient transformers. But again, that adds cost. There is a happy medium typically as far as what does the product cost versus what does it save you in energy over the course of its life. There is always a capital cost for equipment, but then the operational cost plays a huge role. And we'll touch on that a little bit later when we start talking about efficiencies and paybacks and what have you. The Department of Energy 2016 mandate outlawed what was called the NEMA TP1 product, which was an attempt, but a failed attempt at making more efficient transformers by manufacturers because there was no authorities overseeing that. The primary requirements for the test is that, and these are some shortcomings of Department of Energy, but they had to make some resolutions with the manufacturers because they were pushing back on some of this because they knew their product would go up in price. But one of the points is that now they test a single point on the transformer for efficiency. They load a transformer to 35% of its rated capacity of a linear load, which is a non-electronic load, 100% resistive linear load at 35% load, and they record its efficiency. Efficiency is merely the power in compared to the power out, and those losses divided by the power in is what your efficiency is. So if it's a 100 kVA input and the output load is actually 95, there's 5,000 watts of losses. Therefore, that unit is 95% efficient. That's a bad representation because that is a very inefficient unit, but that's how they calculate it. So at 35% load, linear load, they take that reading. That reading must meet a certain efficiency amount or higher that's mandated by Department of Energy. And every size transformer has a different efficiency requirement. Typically, it's in the 98, almost 99% efficient, which sounds great, but you could still be talking about a product that is losing either 150 watts of energy or 850 watts. The unit with 850 watts of energy loss could still meet the mandate, could meet the requirement. However, the one that's 150 is just an ultra high efficient. So that amount of difference could save you a good bit of money because that loss is 24/7, 365. And whatever your electric rate is, you can do the math and determine how much that loss is costing you. The other item test requirement, as I said, is the linear load test. We know now that virtually every application for a transformer has what's called nonlinear load or electronic load. That affects the efficiency of the transformer in a negative manner. So as you add nonlinear load to a transformer, you also lose efficiency. There again, you need to be aware to know that if it's going on a nonlinear load, it's not going to necessarily meet DOE 2016. There are products out there that still meet or exceed 2016 with nonlinear load. That's what we recommend customers to strive for, because now you are still saving that energy you thought you were saving from before. The last point that really bothers me personally a little bit is manufacturers that build transformers only have to submit 5 transformers for their annual certification process to show these 5 transformers for each size meets or exceeds the DOE requirements. The problem is they can handpick those 5 and they can reuse those 5 year over year. However, what they build on an assembly line then doesn't have to be tested before it ships out to make sure it meets the requirement. And the majority of those do not, but they met the requirement of supplying the 5 and getting approved by Department of Energy as saying they're compliant. That is almost a bait and switch in my mind, but that's how it's written now. We just recommend that customers or engineers require the transformer be tested before it ships to show that it meets DOE. Now you know you're getting a product that meets what you specified. It's not a hard test. Manufacturers can do it. Many don't want to because it's an added step for them and it costs them money. But some manufacturers have no issues with it and will provide that test report. So linear versus nonlinear performance, what we're talking about when we talked about the loading is you see these curves. The linear load curve and that dotted green line is where Department of Energy tests the transformer. So in this case, we've got a transformer that's a little over 99% efficient per DOE. But as soon as we start adding nonlinear load, which shows up as the K7 loading curve, you can see how that efficiency drops way off. You can build a transformer to handle that nonlinear load and stay at or above the 99%. But again, that typically is a higher performance, could cost a little more for that feature, but at least you're getting what you expect to be saving as far as energy. The market response to the DOE primarily pertains to how manufacturers went about providing products to meet the DOE requirements. When you manufacture a transformer, there are really 2 components to a transformer for the most part. It is a magnetics transfer of energy. So you have a core, transformer has a metal core that is wound with conductors on a primary side and on a secondary side. It's a very simple math calculation in that if I have 100 volts in and I want 200 volts out, and my primary coil has 100 windings, so I have 100 volts in, 100 windings of my conductor on the primary side, and I want 200 volts out, I need to have 200 windings on the secondary side. That core needs to be wound 200 times with the conductor on the secondary to give me the 200 volts. That's bare minimum, basic transformer technology. By designing the product to meet DOE, manufacturers can lower what's called the input impedance of the transformer, which makes the transformer more efficient, okay? But there's a drawback to the low impedance, as well as a value called high inrush, or the inrush current of the transformer. By the design of the transformer, When a transformer is energized for the first time or every time it sees energy being applied to it, to build the magnetic flux or the magnetic wave around those coils, it takes a very high amount of power for a very short amount of time. And that's called inrush current. How much current does it draw when it first gets turned on? This, between the high inrush and the low impedance, by playing with those designs, you can get a product that meets DOE. And it's a very easy, inexpensive way to meet the DOE requirements. The problem is that what it equals is typically nuisance tripping on your transformer, meaning the circuit breaker that's supplying the power to the transformer will see one of these issues, primarily high inrush current. And when that unit is energized, it could trip the breaker, thinking that it has a short circuit or a high load, so it's protecting itself. So it trips that load or that transformer, and you have power, or you've lost power to that transformer. There's issues with that. So there are ways to manufacture transformers and not have a low impedance or a high inrush. But again, typically by doing those designs, it's a more labor intensive construction, and typically the product costs a little bit more. So it just keeps going back to the higher performance is going to cost a little more, but the payback we'll touch on in a minute will show that it's well worth the little bit added cost up front to save you money over the course of the life of that unit. What has been found over actual tests in the market, and I'll explain why we're looking at loading on transformers, is because where Department of Energy tests transformers at versus where they're actually loaded in application is a far cry from being the same. And I'll show you in a minute on the curve where the actual loading is and how less efficient the products are at that point. So what we show here is transformers that are 5 to 20 years old, typically are the worst performing, have the most losses of all the transformers available, meaning the more current transformers are worse than older transformers, 20 plus years, and are definitely worse than the ultra high efficient transformers. This is actual data from tested 75 kVA transformers in facilities, and we've got data for all sizes of transformers and all types of facilities, and they all reflect the same information, in that you're typically somewhere between 11 to 15% loaded in your facility on a given transformer, which surprises most people. So what are the takeaways on the efficiencies and what have you of DOE 2016? One is the single point efficiency at 35% of linear load is really not a fair representation of what your installation is actually going to see. Manufacturers get to select the 5 units and reuse those. That's, and like I said, is somewhat of a bait and switch, but that's how it's performed right now. Test does not fit everyday applications, meaning you don't have a test that really shows you what you're going to see in your facility day one through the end of its life. And then there's no validation that transformer will actually meet the DOE 2016 requirements, meaning there's no test to prove that that unit that's being shipped to your facility meets the requirements. K-factor ratings we'll touch on. I do want to step back. I did not answer one of my own questions or statements about the percent loading of a transformer. So they're 11 to 15% loaded versus 35% loaded. I want to step back real quick and touch that on this slide. And where I'm talking about is that dotted green line is the 35% where DOE tests. But if we're at 11% loaded on the linear load, if it's tested and meets 99% efficient, at 10% loading, it's only 98%. And a lot of people think 1%, that's not a lot. Well, 1% load on, let's say, a 100 kW transformer, or say a 112.5 kVA transformer, that's 1120 watts of losses that you're adding to the standard losses of that unit. So it is going to put out 1100 watts more of energy, lose that you're paying for but not getting the advantage of. A lot of people have a hard time understanding what 1100 watts is, but just take a large hair dryer and figure you're going to turn it on full blast and let it run. That's 24/7, 365. That's what you're losing. So keep in mind, it can add up to quite a bit of energy loss and cost to your facility, especially when you start multiplying these out amongst all your transformers. So to go back, okay, just wanted to touch on that. I apologize for missing that. K-factor ratings. K-factor is a relationship of the nonlinear load versus linear load. And all it really means is that electronic loads typically produce harmonics. Harmonics are a somewhat can be a detriment to your facility and your equipment. It causes an induced additional current on your equipment, which can derate them. So a standard transformer under linear load can handle 112.5 kVA worth of load. Let's just use that as an example. If I have nonlinear loads producing harmonics, I now could have my transformer derated due to the added currents it induces into the transformer. That transformer is no longer got the capacity of 112 kVA. It may only have capacity of 100 or 90, depending on the level of the harmonics. This becomes a major issue when your harmonics get very high. What a K-rated transformer does is they oversize the transformer to handle or deal with those harmonics, meaning a K13 transformer, 112.5, may actually be built to around 130, 135 kVA size, knowing that it's only going to need to handle 112, but it'll have those harmonic contents. So all it really is overbuilding the transformer to handle that added load from harmonics. The problem is you're not eliminating harmonics in the nonlinear load. You're just dealing with it. So K-rated transformers tend to cost a little bit more because, again, they're just oversized for that capability. So there are things, I don't show it on here, there are what's called harmonic mitigating transformers that actually eliminate the harmonics as opposed to just dealing with them. So when you get into situations where you feel you have a large nonlinear load component, you're welcome to reach out to us or a manufacturer and ask them about harmonic mitigating, or how do you cancel out the harmonics and get rid of them. The UL 1561 requirements as it pertains to K rating. This is where Underwriters Lab kind of dictates what is acceptable in certain applications. And what we really want to point out here is Most manufacturers will sell and want to sell what's called K1 or general purpose DOE 2016 compliant transformers. That's the least expensive transformer they manufacture. They want to be competitive on every job, so they want to use the least costly product on every job. The problem is UL recognizes that these transformers are not rated for nonlinear loads. So if you have any electronic load on that transformer, a K1 or general purpose transformer is not UL listed for that. Now, this could cause liability issues should there be a problem with that transformer, and rarely there are, but should there be, it's a misapplication, and insurance underwriters, certain authorities will note that, well, that product wasn't intended for that use, therefore your claim is invalid. If you're claiming an insurance claim because a transformer burned up and caused damage, but if it was misapplied, that's going to be on the customer, and we try to avoid that. Even though that's extremely rare, it could happen. So they make a point that nonlinear loads require K-rated transformers, but yet they don't tell you what the K rating should be for the different loads. So that's really where the engineer comes into play, into making sure he's protecting you from the loads you have in your project or in your facility for that design. And I would lean on them to help you with that and make sure that it's covered. And most engineers will protect you in that respect. So kind of a question I threw in here, but we've touched on it a little bit. What is the average load of a transformer? Again, it's typically at between 10 and 15%, which really doesn't fit, like I said, what the application is for DOE 2016. Some of these slides we will go through fairly quickly. Not to reiterate what I said earlier, but here's a better representation of where typically transformers are loaded versus where they're actually tested and rated by a Department of Energy. And this applies to almost every size transformer in every facility. It's not conducive to only schools or only hospitals or only data centers, what have you. It's pretty much widespread that loading levels are very low. You can have some specific applications where you know the loads are and what they are going to be, and they become higher, much higher loaded transformers, which is good for trying to get closer to that peak of 35% loading. But as you notice, the efficiency of a transformer also drops off as you get higher loaded, a highly loaded transformer, unless you build a transformer for that specific application, which a few manufacturers do, most don't. That being said, this is kind of a representation of three different transformers that are built or that some manufacturers will build that pertain to different loading. So the green line is a transformer efficiency. Now this is, if you keep in mind, this is a loss, a added percent reduction. So as you see the 40% on the left side or 42% for that green line, that is representing that transformer at 0% load is 42% more efficient than a DOE 2016. So keep in mind, this is looking kind of at the peak. But as you go in your percent loading, you can see how most of these transformers, well, all of these stay well above the DOE requirement, but they do drop off. So the green line is a transformer built more for a lightly loaded transformer, less than 20%. The efficiency is much higher, saving you much more energy, so you have less losses at that level. to where the blue line is a transformer that's more of a medium loading, meaning it's a little more um, level on all loading of the transformer. So therefore, if it's a 50% loaded transformer, it'll keep your efficiency up more so than the first transformer, the green line. And then the last one, what I call the black line, that is a transformer that's more built for a highly loaded transformer, where I've got a specific load or application that I know my 112.5 kVA transformer is going to be loaded most all the time at 80, 90 kW worth of load. That being said, that transformer is built and designed for the higher loading applications. All of these don't change the cost of the transformer, but they do change the internal construction of it. And where one transformer needs more of one construction design, the other one needs that in another area. So that's why most manufacturers that do this can provide different levels of transformers, applications of transformers for the same price. It's just where do they spend their money in the construction? So just keep that in mind. Transformer retrofit applications. One thing I want to point out is transformers are one of the few products in a facility that once you install it and energize it and run it, you typically don't touch it, don't see it, don't care about it for the life of the facility. And in some cases, as far as hospitals, schools, government buildings, those facilities will always be a hospital, a school, or a government facility. Therefore, those transformers could be there 30, 40, 50 years from now, still doing what they did, or hopefully doing what they did day one. Problem is, transformers become a very good shelf for storing products, as you can see in the picture. Never want to see things stored on a transformer, but it happens. The problem I see, besides something could leak or what have you and cause an issue on that electrical piece of equipment, is if it's a not very efficient transformer, the top of that transformer could get very hot, therefore affecting those whatever you have stored on top of the transformer, as well as it also acts as an insulator, preventing the transformer from dissipating what heat it's generating. An ultra high efficient transformer has very little heat loss because of its very low energy loss, but still it's an issue. But when you have retrofits, what you tend to do is you want to test the transformer you have to see exactly what the load is, what component, is it a nonlinear harmonic load? Is it not? And then match that load to the closest transformer that will meet that need, that capacity, and keep the loading level up so we can hit that higher efficiency rating and fit in the space. All of which, when you do that and do it properly, yes, the new transformer is a capital cost to replace the old transformer. But even with the cost of that transformer, the amount of energy it could save you before you go and purchase the transformer, we could calculate this out. The amount of energy it saves you will then more than pay for that unit over the course of its life. And typically it's a 3 to 5 year return on investment. So after the 3 to 5 years, you're now saving that money moving forward. That is a very short payback and high energy return if you start looking at the course or the life of your facility. And a transformer takes no maintenance. You're not replacing a lamp, you're not replacing components in it. It just sits there and runs typically. So that being said, one of the things we kind of point out is make sure that that transformer is warranted for that time period. Some manufacturers will warranty transformers for 25, 30 plus years because they know what you're buying, they know what they've built, and it will last that long. If they're only supplying a 1 to 4 to 5 year warranty, be a little suspect. That transformer should last 30 to 40 years regardless. Just be conscious of when you're doing retrofits of the footprints and what have you, which we can help you with, or an engineer can help you with, if that's an interest to you. Transformer options. I'm going to go through this pretty quick so we can get to the end and have any questions or answers. So transformer options that we see are beneficial to customers, depending on whatever your facility is. One of which is the transformer sizes. What we're talking about here is on the left-hand column, the standard kVA. That's standard transformer sizes from most manufacturers. Those are the sizes they manufacture. The blue column or the additional kVA column are additional transformer sizes that some manufacturers will manufacture. At no additional cost per se. Their cost is, so a 50 kVA is cost between a 45 and a 75, but that's the capacity. The reason these are important is, as we talked about the percent loading, I'm going to use the example of a 150 kVA. If I have a 150 kVA transformer and it is, let's go on the high side, that it is loaded to typically to 15%. That would mean that that transformer's load that it'll actually see is 20 kVA, 22.5 kVA. But in design practices, if an engineer is designing the space and his load on that transformer, on his calculated load that he thinks that transformer will see is, let's say, 120 kVA, he's going to apply a 150 kVA transformer. The problem is if he sees that it's 151 kVA of load, after he handles any future load that could be added or fudge factor, he has to jump to a 225 kVA size transformer. That's a 50% increase. But if I know in real world that 150 kVA would have had 22 kW worth of load, that now instead of being 15% loaded on a 225 kVA, that's only 10% loaded. So therefore your losses are going to go up because the loading went down. So that's really what we're pointing out here, is right sizing a transformer for your load by having the ability to build different size transformers. There are a few manufacturers that will build any size transformer you want, and the cost is generally in between the cost of standard transformers of these standard sizes. One of the most beneficial options on a transformer that can be provided are hinged lockable doors. Reason being is if you have any issues with a transformer or fear you have issues and you need to thermally scan the transformer or possibly see what could be causing the added noise or what have you, and you have a trained professional or an electrician look at it, most transformers, they have to pull the front cover off, remove several screws, pull the front cover off to get to the inside, to see inside the transformer. So if you go to existing facilities and look at older transformers, they almost always are missing screws because you take them out, you drop one, you lose it, you forget, they never put it back, they never add one. In this case, there's no extra tools required. You can lock doors. Some provide lockable doors, some just have hinge doors, but you can open the door, see what you need to see, thermally scan it, whatever you're doing, close the door, go to the next one. The cost of the doors is very low, typically $100, $200 for a set of doors for transformers, but it is one of the most advantageous pieces of equipment or option on a transformer you can get, especially if you thermally scan your equipment under a maintenance contract, either annually or every 2-3 years or what have you. Another option is IR ports, infrared scanning thermal ports. If you do scan your transformers regularly, you may want to look at a IR port for the transformer so you don't have to open the door or open the front of the transformer. There are two kinds. There's a window, little round window that can be placed. Problem is those you need to require multiple windows to see all the points of interest inside of a transformer, or you have what's called a rotatable IR port that will see all those areas with one port that you can set your camera on and rotate it and be able to see all of the key points in the transformer to see if you have a heat problem or a resistance problem. Integrated breakers. Typically, transformers are fed from panel boards, and then that transformer feeds a load, whether it's another panel board or what have you. In this case, providing integral breakers on the primary or secondary side could aid you in having one transformer maybe feeding two sources, two loads, as opposed to having a transformer per panel board. Let's say you could actually have one transformer with two internal secondary breakers. Each one feeds a different panel board. You save equipment, you save footprint, you save cost of an additional transformer, and you save those additional losses because now we can drive the load up on a transformer more so. Instead of being 10-15%, if I have two panel boards on it, I should be in the 20 to 30% load. Well, that's right at your sweet spot of the design of the transformer. So therefore my losses are less. That's a very advantageous way of saving equipment and capital cost on a project, is providing a larger single transformer feeding multiple loads. High performance transformer integration. All we're talking about here is you could have, again, transformers that may feed a panel board and or may also feed another piece of equipment, as in overhead busway or a specific load, and the breakers, primary or secondary, can do it, but also have transformers that are multi-tapped. So if I have a 480 volt circuit to the transformer, you can build the transformer to provide one breaker supplies a 120/208 volt load. Another breaker may supply a 240/415 volt load. So that's more specific application, but that is used a lot on industrial facilities and what have you. Another option that's highly recommended is integral metering in a transformer. As the federal government is wanting to validate savings, if you say you're going to save this much, you need to show them that you're saving that much. The only way to do that is metering. You can provide an integral meter into a transformer and do just that. Or you could log, the picture on the left is of a data logger that sits in the transformer. You access it through a USB port in the front, and you can download what is the loading on that transformer, what's its efficiency, and see that log report so you can determine if you're adding load later to that transformer, you already know what your existing load is, as opposed to having to test it for 30 days to get that load. This is already providing that for you. This is a big plus for schools and hospitals because things are always changing. They're always adding load as the school's capacity gets larger and they need more power. They add load. This is a way to do that very easily. Real quick, power distribution units is primarily a lack of better terms, a transformer and the panel boards that the transformer feed all in one box. I only wanted to touch on this in that typically you would have a transformer that feeds a panel board, or in this case, a distribution board on the left, and it takes up room in the electric room or the space it's located. It takes added install costs because the contractors must interconnect those two, set them, feed each one. To where on the right side is a power distribution unit, which is the same equipment. It's one single box with the transformer in it, with the panel board built into it. So it comes, gets set in place. It takes a much less footprint. So you're saving real estate space, but also everything internally is already wired. So therefore, the contractor wires the PDU like he would the transformer, and then goes out of the PDU to his loads. He doesn't have the interconnect between the transformer and panel. Another big advantage with that is you can also build what I call an energy station, such that I need to add load or add distribution in a specific area. And I need both 480, 277, 480 volt power in that area, as well as 120, 208, or any other voltage in the secondary. I can provide an energy station that is like a PDU, but it includes the 277, 480 volt panel built into it, which then feeds the transformer, which then feeds your 120, 208 volt panel. All of which is, again, in one box, less installation cost, much lower footprint, and all of these products can utilize ultra high efficient transformers. So you get the best of all worlds moving forward. I only wanted to touch on that because there's a lot of new applications, new products hitting the market that reflect these kind of changes. We've been doing this for several years with engineers and customers, and it is a huge savings to them, especially on real estate space of electric rooms or places they're putting this equipment. So it all, if you ever have a thought of this kind of application, you're welcome to reach out to me. I'll give you some information as to what it is and what it would be specific for your application. That being said, this is kind of a wrap up of where we're at, and the things that you need to be aware of when it comes to specifying or purchasing or reviewing transformers for your facility. Almost every facility has transformers in them. So it does get important to make sure you know what you're looking for, what you're asking for, or what to ask for. So one's the kVA and voltage of the transformer, the linear efficiency meets or exceeds DOE. Ideally, you want to require it to exceed DOE, not just be the bare minimum. What is the nonlinear efficiency of that transformer? If they don't want to provide you that information, then typically a manufacturer is hiding something. They don't want you to know. So just keep in mind, what is the real world application going to do as far as my efficiency of that product? The things highlighted in red, the first one here is inrush current. You need to make sure the inrush current is maximum 5 to 10 times the full load current of that transformer. Gets a little technical here, but the engineer should know this information. But if you're asking, you may just want to tell the engineer or the manufacturer, this is what I'm looking for. Show me what your inrush current is. You can use this as a reference. You can reach out to me at any point and I could help you with, yes, that's good. No, that's not so good. Here's the problems. Same with impedance. The impedance of a transformer should be in the 3 to 6% range. As I said, some manufacturers can lower the impedance to meet the DOE, and they could be in the 1.5 to 2% range. That can cause some serious issues with the functionality and safety of your electrical distribution. Again, an engineer can help you with this. We can help you with it, what have you. Temporize, not as important, but the lower the temporize of the transformer typically means the more efficient that transformer is. So most standard transformers are 150-degree rise C rating. Typically a 115 to 130 is pointing out that it is probably a little more efficient. And if you dig a little deeper, you can find out how much more efficient. Again, hinge doors, rotatable IR ports, integral meter, what have you, are all added options, not necessary, but they can play a big role in the future and save time or effort or what have you on your part. The last, and this is probably one of my most important criteria, is the nonlinear load test of a product, of a transformer, to validate that they meet the spec. This is where you're telling the manufacturer or the supplier, I want that transformer tested before it ships to my facility, proving that it meets what I've specified. Now you as a customer know you're getting what you're paying for. If they can't meet that or can't provide that test, then they are more than likely not providing a product that meets that requirement. So now they are selling you or providing you a product that may not meet your specification. This is not a test that is a costly test for them. Some manufacturers may charge $100 or $200 for this test, but when you're looking at the cost of the transformer and it being there for 30 to 40 years, I highly recommend you require the test report. Some manufacturers, the ones we represent, we generally don't charge for this test report. The manufacturer does it regardless before they ship it, and they'll provide it as what we call closeout documents, showing that it was built, it was shipped. Here's the report for that, so you can assure that it meets the requirements. That being said, that's the conclusion. Hopefully it wasn't too long-winded. If you have any questions that you've jotted down over the time to ask those questions, we'll try to answer them. And if you come up with any questions or comments or need information later, you'll have my information to reach out to me, or like I said, reach out to your engineer that's working with you on the project. They are a great resource. But I appreciate it and look forward to answering anything you have. Thank you very much.
Okay. There we go. Okay, so I noticed that Mike Rasmussen put yikes in the middle of the presentation. It's a lot of information. So if you are taking a whole bunch of all of this in, awesome. If you feel like you need to sit through this again, good news. You will be able to. You can come back into the virtual platform and you can watch this at any time. But at this moment, we're hoping that we can get Ken to come in and start answering some questions. I'm not sure if he's able to do that. So we're going to do some things a little bit the old-fashioned way. And let's see if we can get Ken on the line and answer your questions. If you have those questions for him, go ahead and start putting those in the chat feature. Ken, are you with us?
Yes, ma'am.
All right. Can you guys, can y'all out there let me know if you can hear Ken? Can somebody give me can you say hello again, Ken?
Hello, KClark here. I appreciate it. Sorry for the difficulties.
It is not a problem. Guys, can you hear all of us? I've got somebody type in. I think they can. Jeff, yes, they can hear you. So is there anything that I know that you recorded this a while ago. Is there anything that you would like to add to what you said? Is there anything that you would like to do some closing thoughts? And that's going to give some people some time to type their questions in for you. But is there anything you'd like to add?
Well, just, I know it's a lot of information, And I just want everybody to know that we work very closely with engineers, end users, customers, what have you, contractors. So at any point, if you ever have any questions, feel free to email me, call me, what have you. I'll help you with information. It is a lot of smoke and mirrors out there in this industry with products. We try to level set that so that a customer knows there are some good products and there are a lot of products that are lesser products. So we try to help mitigate that and give you the best unbiased info we can and let you make the decision. So by any means, just don't hesitate to reach out to myself, and we'll be happy to help you with any information. We do it every day with engineers and customers. So that's mainly it. It's a lot of info, but if something comes up later, at least you can ask, at any time and be happy to help.
Yeah. I just put your email address into the chat feature of this session so that anybody seeing it right now, anybody coming and seeing it later, they will have access to your email and they can reach out to you. But you guys can also reach out to Ken through the networking section of the virtual platform. This platform will be open from now until December 31st. And so if I know this was a lot of information, if you feel like you just didn't process all of it, because we've had so much information this week, come back to it. You will be able to access this from the virtual platform anytime you want from now until December 31st. Ken's information will be on here all the way through December 31st. Reach out to him either through networking or through his email. He'd be happy to talk to you about your specific situation, about your specific questions, and how it relates to you specifically at your organization. Ken's great. And so reach out to him at any time. I'm not seeing any questions. Does anybody have any comments while you're out there? Just anything? I'm not seeing anybody type anything. I think it was really comprehensive, Ken. Thank you so much for all of that information.
My pleasure. I appreciate the platform, and I'm a huge supporter of TEMA.
Yep.
And
yes, you are.
I'm glad to see it. So.
Yes, you are. And hopefully April of next year, we will all be able to get together in Waco and do this in person. So instead of having to deal with multiple different electronic vehicles to get the information out. But I appreciate your flexibility and I appreciate all you do for TEMA.
Well, thank you.
All right, guys. Well, with that, I'm not seeing any questions come in. We just really do thank you for your time, Ken, and for the presentation. And please, guys, don't forget that we have our closing panel session and our ending to the live conference here in just a few minutes. Make sure you get on to that and that you can hear the panel and see kind of a wrap up of conference. But other than that, we really appreciate all of your time and we'll see you in just a few seconds. All right, bye-bye.